from the University of Sherbrooke is going to tell us about classical simulation of quantum many-body systems with tensor networks.
Okay. Thank you very much, Andrew. So I'd like to thank the organizers, first of all, for putting this together and having me here. So today my talk will be kind of an overview talk on some of the limits of what we can do with classical simulation of quantum many-body systems. So the first question we might ask is, why do we care about classical simulation? And at least for the moment, like quantum computers have made a lot of progress, quantum simulators have made a lot of progress, but they're still not quite there. And even if they do become much better, classical computers are still going to be more abundant and cheaper. So it really makes sense from a practical perspective to explore what can be done with classical simulation methods, even if these things do become much more feasible. And from a theoretical perspective, like more fundamentally, we want a good understanding of what classes of quantum system can be simulated and why. So even if these things get really good, we still want to have this theory of what makes quantum systems difficult to simulate classically. Okay, so this question of what can be done classically really depends on how much, a lot of this question depends on how much rigor you want to bring to it, whether you're a computer scientist or really a physicist. So if you're at the high level of rigor, you care about efficient simulation and theory, you want algorithms that provably converge in polynomial time, you want rigorous error bounds, you want to classify complexity classes. You maybe don't care that things aren't practically viable, like I was at a talk a few weeks ago and they were discussing an algorithm that scaled as the number of qubits to the power of 200, which is still technically efficient, but is not going to be much use from a practical perspective. When you go to the other side, if you want efficient simulation and practice, you want good results on sort of reasonable time on current hardware. You may not necessarily care whether you can prove things or not, or whether you even understand why something works. So just to set the scene today, we're going to be somewhere in the middle where we want methods that could be or are practically viable, and yet also still have a good understanding, a good theory of why these things work, if not rigorous proofs. Okay, if you do want to understand more of the practical side of things, I would suggest this paper sponsored by the Simons Collaboration on the many electron problem. So comparing a whole bunch of methods for the two-dimensional Hubbard model. So you have a ton of methods, say comparing the ground state energy. So coupled cluster, DMRG, Monte Carlo, Hartree-Fock, all kinds of things. And there's a follow-up paper in which they compare methods for a 1D hydrogen chain. Again, a ton of methods. They go through all the details of what works and where, many comparisons. Okay, so let's get started on the talk proper. Okay, so we have a qubit, a two-level quantum system. Of course, a state on the qubit is just specified by two complex numbers, complex amplitudes for the 0 and the 1. For 2 qubits, we have 4 numbers. 3 qubits, we have 8. 4, we have 16. Okay, so a wave function in a local basis on some number of qubits is described by some tensor, which is just a coefficient for each of the binary strings of basis states. Okay, very simple. So clearly we need exponentially many parameters to fully describe a wave function in this local basis. So what can be done classically if we want to do everything exactly? So a 5x5 lattice, very easy on a laptop. 6x6, we could do it on a workstation, maybe if we have around 100 gigabytes. 7x7, this is roughly the limit of Lanchos today. Like if you have a very powerful supercomputer, if you maybe have many symmetries in your problem, this is something that you could do classically. However, of course, this is exponential scaling, so things roughly get out of control. We're never going to be able to do big systems this way. So 10 by 10, we have the number of bits in memory is comparable to the number of atoms in a human being, or the number of atoms in a solar system for a 14 by 14, or the number of atoms in the observable universe. Okay, so describing an exact wave function on n qubits, this is not a route we want to take. So we need to make some approximations when we do this. And of course, there are many different types of approximations you can make depending on the physics. One of the most reasonable is to make approximations in terms of entanglement. We can see very easily why this may work. So if I have just a generic entangled state on n qubits, it's described by this 2 to the n coefficient tensor. However, if I have a product state on n qubits, it's specified by order n parameters. So I just describe each state individually. So you can see here that the difficulty in representing a quantum state is somehow related to the entanglement. If I have no entanglement, then it's just a very simple product state. If I have so there may be some hope of sort of going in between these two extreme cases where I can still have some amount of entanglement and still do things efficiently. Okay, so this brings us to the question of how much entanglement is present in relevant quantum states, the types of things we may care about. And for the purposes of today's talk, we're going to think about quantum states, quantum many-body systems on the lattice. So imagine I have a lattice 1D, 2D of spins or qubits or fermions, and I'm just thinking about having a local interaction. So things interact with their neighbors or their next nearest neighbors, so forth. So local interactions, and we're interested in ground state physics or very low energy physics, low energy excitations. Okay. And in the vast majority of cases, the ground states are entangled. They're not going to be simple product states. However, there's lots of structure in this problem given from these local interactions. Okay, so I have a system where the spins interact locally. The structure that this gives to the ground state is that spins will be very strongly correlated or entangled with nearby sites, but less and less strongly correlated as from sites further and further away. Okay, so this is sort of our intuition. We can make this more rigorous. The one way to think about this is in terms of block entanglement entropy. So the von Neumann entropy of a reduced density matrix for some subsystem of this lattice. So I'm imagining I have a state on this lattice. If I just chose a random state from the Hilbert space, say according to the Haar measure, I would get the entanglement of the block would scale as the size of the block directly, so a bulk scaling. What we observe and what has been sort of more formally proved by Hastings is that if we have a 1D gapped Hamiltonian, the entropy scales as the boundary of the block. So we can think about this. We have some short correlation length. It's only things near the boundary of the block that are contributing to entanglement, so it doesn't matter how big this block is. The entanglement still saturates at some upper bound. Okay. If we have a 1D gapless Hamiltonian, the most usual case is that we have a logarithmic scaling of entanglement. Okay, so we have growth entanglement that grows with the block size, much less than the bulk law, but still growing without bound. So these correspond to conformal field theories in general. However, there are other behaviors possible. In the case of gapless, you can have very sort of pathological things, but this is the most typical behavior. Okay, so gapless, you have polynomial correlations, so things even deep within the block still contribute to this block entanglement entropy. Okay, for 2D systems, again, you have something very similar, where if I have a 2D lattice, some state, ground state, if I'm looking at how much entanglement does, say, an L by L block have in this 2D ground state, this is not something we can prove rigorously anymore, but at least for, say, this is observed in the vast majority of cases, and we have some, say, rigorous proof for free fermion systems. So if we have a gapped Hamiltonian, we have a boundary law or an area law, so the entanglement is just the size of the boundary. Okay. So again, the intuition is the same. Things within the bulk aren't contributing to the entanglement or aren't contributing much to the entanglement. If we have a gapless system where I have a finite number of zero energy modes or a Dirac point in my Fermi surface, then I still have a boundary law. However, if I have a gapless system with a 1D Fermi surface, then I get a logarithmic correction to my boundary law. Okay. So we can have this sort of table of entanglement that we find in ground states of local systems for 1D systems and 2D systems. And what we see is either we see a boundary or an area law, or with some like slight correction, a logarithmic correction. And Jens Eisert has a very good review paper on area laws in quantum systems if you want to learn more. And this is what gives us hope in that this is something we can do efficiently, is that these ground states of local systems have much less entanglement than a generic entangled state. So clearly we can't just simulate arbitrary things in this regime, arbitrary quantum systems. However, these cases are very, very special, have some very special properties, so it might be feasible to try and do these efficiently, classically. Okay, so can we find ways of parameterizing area law or boundary law states efficiently? That's the goal. Okay. And one very productive way of doing it is using these structures called tensor networks, which are, okay, so just schematically before I go into detail, so the idea is a typical or a generic wave function is described by a tensor with exponentially many parameters. So this is some very complicated object. I'm going to break this down into a product of simpler objects, a product of small tensors that I can describe each of these efficiently. Okay, so just to make things very clear, I have my quantum state, say on n qubits. I'm describing these complex amplitudes in this tensor, okay, with n indices. Okay, so if I just fix each of these legs, it tells me a complex number according to relating to the amplitude of some state. And now what I'm going to do is just very quickly, we're going to use a graphical or diagrammatic notation to represent these objects. Okay, so if I have a tensor of some number of legs, it's just a blob with four lines coming out of it. Whenever two tensors share a line, this represents a summation or a contraction over this index. Okay, so we're going to consider states where this coefficient tensor factorizes into a product of smaller tensors. Okay, so if we try and do things with equations, they get very complicated and difficult to understand. But if we draw this out, okay, so we've just partitioned sort of linearly following the 1D lattice this tensor into a product of tensors, okay, where we're summing over these internal J indices. Okay, and we'll go into more detail about this later on. So schematically, we can think about it. We have for this generic entangled state, arbitrarily high entanglement. It takes exponentially many parameters to describe this. At the other end of the scale, we have a product state. So this is very boring. We have no entanglement here. However, we have an efficient representation with order n parameters describing the state. So the tensor network is an interpolation between these two extremes. Okay, so we have some bond dimension chi, we call it, which just is the dimension of this index. If chi equals 1, then we have a product state. If chi is exponentially large, then we can recover any state up here. So the hope is that for some reasonable values of this bond dimension, we still get some entanglement, and that this is enough to do some interesting things. Okay, so we can really interpolate between these two extreme cases in some controlled way. So given, okay, and this one here is called a matrix product state, just this one-dimensional sequential sort of partitioning of this state tensor. Okay, so given this general idea of cutting this big coefficient tensor up into a product of smaller tensors, we now can sort of see the rules of the game. There are many ways we could try and cut a state tensor or represent it as a product of smaller tensors. What makes a representation useful, and what ones should we consider in doing this? Okay, so in doing this kind of decomposition or this kind of representation, we want to have an ansatz that's compatible with the properties we expect in our state. So we want the correct entanglement or correlation functions or mutual information. So this is the one we'll focus on today, entanglement entropy. We want efficient algorithms for manipulating these structures. So I want to be able to optimize the parameters of these tensors in some way as to give me a good approximation to the ground state of the system I'm interested in. And we want to, of course, be able to extract information, expectation values, correlation functions efficiently from these structures. And usually these two things sort of go hand in hand. That if I can evaluate things efficiently, then I have good ways of optimizing the parameters as well. Okay, so these are two structures we're going to compare from the beginning. Both structures for 1D lattices of n sites, both structures that have order n parameters. So matrix product state, and this one called multi-scale entanglement renormalization ansatz, or mirror. Okay. So it's a much more complicated structure. However, we shouldn't be too scared. I just have some 4-index tensors and some 3-index tensors. Okay, and I organize my tensor network with an extra scale. So this is a length or an energy scale. Okay, and I'm just, so each layer has the structure, and I have log, if I have n sites, then I have log n of these layers before I have no more sites left and I stop. So this is related to a coarse graining transformation, but we don't have to think about that for today. It's just some structure of tensors connected in a network. So is there some benefit for having this more complicated structure that has this, this extra connectivity, say in terms of entanglement? So let's look at these. So the question we should ask is, how much entanglement can I reproduce with this type of structure, this matrix product state? So I have a chi-dimensional index connecting the tensors. I want to know how much entanglement can this block A possess. Okay, so each dimension or each index carries at most log chi entanglement. A and B are connected by only 2 indices, and this is independent of the size of A and B. Okay, so I have a strict upper bound. Any state described by this matrix product state, the entanglement for some block of sites is strictly upper bounded at 2 times the log of the bond dimension. Okay, so this is a constant that doesn't depend on the system size. Okay, when I look at this more complicated structure, if I ask how much entanglement can I have between A and B, at least I can get an upper bound for what this entanglement can be by asking the question of what is the minimum number of wires I have to cut in order to separate this region A, or the indices contained in this region A, from B. Okay, so here I need to cut at least 4 indices in order to separate these 2 parts of the network. If I increase the size of A, here I've doubled the size of A, then I need to cut at least 6 indices to separate A from B. Okay. So this is an upper bound, but in practice this upper bound can be saturated, or at least the scaling of it. So what we see here is, again, the entanglement depends on the log of the bond dimension, but it also scales with the size of the block we're trying to represent. Okay, so larger blocks can have more entanglement. And when we draw these pictures, this is how you should think of it, is it's really a geometrization of the entanglement in a wave function. So these indices carry entanglement between different parts of the system. The more indices we have, the more entanglement we can have, but potentially the more difficult it can be to actually manipulate these structures and to evaluate them. Okay, so here are my 2 example structures for 1D. You can see where each of them may be useful, and that one reproduces the strict boundary law for entanglement entropy scaling, one reproduces this logarithmic violation. And in practice, we find this matrix product state is very good for representing gapped 1D systems. You can scale to very large system sizes very accurately. And this mirror structure is very useful for gapless or critical 1D systems, and that you can really reproduce the correct properties of a lattice version of a conformal field theory very accurately on large or infinite system sizes. Okay. So this was very hand-wavy. There are more rigorous statements, say thanks to Hastings, for how well this matrix product states works. And more recently, you can have, at least in simple cases, you can have analytic error bounds on how well this mirror works for simple cases.
When you said earlier critical 1, critical 2, you meant first order, second order phase transitions? Or?
Second order phase transition.
So here you mean second order phase transition?
Yes, so things corresponding to CFTs in the continuum limit, for instance. Okay, so these two structures respectively reproduce the expected properties of gapped and critical systems in one dimension. Can we, so this is a statement about these ansatz. Are they useful in practice? Can we actually have good algorithms to optimize these structures? So the problem we usually have is we have some lattice Hamiltonian we want to study. We're going to randomly initialize our matrix product state, and we want some variational algorithm to optimize the free parameters as to give us a good ground state approximation. Okay, so our output is this good approximation. Then we can evaluate expectation values, correlation functions, etc. So DMRG is this most widely used and probably the first sort of good algorithm to do this manipulation, this optimization. In practice, this works very well. There are many other things you can do here as well. This is not guaranteed to converge to the ground state. You can have examples where this gets stuck in local minima. You have ways of trying to avoid this, but however, there is some very nice work, rigorous RG algorithms by Vidic, Vazirani, Landau, and company that actually do have that do provably converge. These are not variational methods over MPS as I understand them, but related to this. Okay. And the same thing for this mirror structure. You have efficient algorithms that work at least most of the time, or it's not usually a problem. We want to be able to extract information from these structures efficiently. And just to give you a picture of what this looks like, so here is the bra and the kit of a matrix product state. I want to evaluate for some observable. I can just do some contraction of the top and the bottom. And then the thing I'm left to evaluate in order to evaluate this expectation value is just a product of a vector multiplied by a matrix many times. So this is clearly an order n operation. This is something that's efficient. Okay, so, and the mirror is similar, and except you have only log n iterations. So these are useful structures. They reproduce the correct properties. These are things we can optimize. These are things we can evaluate in general. Yeah.
Are there existence results at least that say that if the entanglement for all regions behaves? So for MPS there is, but for MERA?
For MERA, no. So unfortunately, this is I would say this is a necessary condition, but it's not a sufficient condition.
There's an example, so I can write down the states that has the right scaling of entropies, but does not have a MERA?
You could write down an example of a state that has the right entropy, but is clearly not correct. So I mean, I could write down a mirror-like structure that has log L scaling, but there are very good reasons why it could not be a good approximation to the ground state of a critical system. So it's a necessary condition, but certainly not sufficient in its own. Yeah. Right. So very quickly, do these ideas generalize to higher dimensions? And the answer is yes. We have matrix product states can be generalized to two-dimensional lattices. These are called projected entangled pair states, or PEPs. And I can build very similar structures to these mirror and higher dimensional lattices as well. And you can very clearly see, or hopefully very clearly, how the entanglement scales in these more complicated structures. Okay, so again, if I just look at the number of wires I have to cut in order to separate an L by L region from the rest of the lattice, is clearly order L indices. So this reproduces the boundary law for entanglement entropy scaling. Okay, so this is what we have so far. These are our entanglement and ground states, we have MPS is very naturally there. 1D mirror is here. PEPs can do this L scaling, and there are examples of PEPs that for critical systems. So maybe you might expect that 2D mirror lives over here. It turns out it doesn't. So this is our schematic representation of a layer of 2D mirror. We just have these 4x4 tensors interlaced. If we ask the question of how much entanglement can be in this type of structure, okay, so just schematically, we're going through the same manipulation where we look at an L by L block and we ask what is the minimum number of indices I have to cut in order to separate this block from everything else in the structure. And you see here I have order L wires I have to cut at the lowest layer, order L over 2, L over 4, L over 8. All of these sum up just to order L. Okay, so we have this very interesting behavior where this 2D version of this mirror reproduces only the strict boundary law, not the logarithmic correction. So this was sort of an open question for some time. Can we reproduce this logarithmic correction to the area law efficiently with some structure that we can still manipulate efficiently? Turns out there is, and we need a slightly more sophisticated class of tensor network. Okay, so a standard mirror is built from sort of this type of building block. We have a quantum state. We interlace the quantum state with some 0 qubits. Okay, so alternating and perform a shallow, say, 2-level quantum circuit. We get a new state and we repeat this procedure, and the mirror is precisely the class of quantum state that can be built by iterating this procedure. Okay. So now, in order to have the logarithmic scaling in 2 dimensions, we need a more sophisticated class of state called a branching mirror. Okay, and the branching mirror is built from a very similar sort of primitive block, except rather than initializing half the qubits in the 0 state, we take some quantum state, interlace them, perform a shallow quantum circuit, and we can repeat this procedure many times. Okay, and remarkably, this class of quantum state is still something that's efficient to evaluate. We can still get expectation values in linear number of steps, linear number of qubits.
Question? Yeah. So I'm kind of unfamiliar, so maybe it's very trivial, but I was thinking if you have a 2D, right? And then let's just start very naively. We just do a normal mirror for every row. So you don't even put contacts between rows, but doesn't this scale like L log n?
I mean, because it doesn't, because
you have L rows, every row is log L.
It doesn't unless you have a product. If you just have a product of 1D mirror without any connections the other way, then that would be L log L. But as soon as if you try and say do a product of 1D mirror and then a product of 1D mirror the other way, and do your 2D transformation just as alternating between 1D, then this only has L entanglement.
Okay, so if you put like one layer horizontal, one layer vertical, and so then we reduce to okay. So
yes, it's not obvious and not clear.
So is there a physics intuition behind this branching mirror? How would you think of what's happening behind this?
Yes, there is. Unfortunately, I won't have time to go into it much in this talk, but so the short of it is, so in 2D, this is useful for cases with a Fermi surface, and you can imagine like different branches are capturing different parts of the Fermi surface. So I'm kind of cutting it into pieces. Or a simpler case is if I had something like spin-charge separation, I can have spin theory go into one branch and the charges go into the other, or something like that.
Yeah.
And are you saying that this branching mirror is still efficient in 2D because PEPs becomes like unfeasible after
2D mirror and branching mirror is still efficient in 2D. Everything is still polynomial in the system size. And when I have these types of structures, so I have a standard mirror, I have this branching mirror with 2 branches at every level, so it looks like a binary tree if I draw the branching schematically. I can have something in between these 2 structures as well, where I have a little bit of branching but not the most branching. So there are, we call this a holographic tree describing this branching structure. Okay, and I have 2D versions of the structure that get very complicated to draw and to implement. But when you look at the entanglement, okay, so I have a 2D branching mirror. I have branches sort of with a binary tree, so 2 branches at each level. When I compute the entanglement entropy from a block, I add up all the contributions. So I have these additive contributions from each branch, and I have more branches at the higher levels. Okay, so when I add these all together, it equates to L entanglement, order L entanglement from each level. So this sums to log L. So I reproduce my logarithmic violation to entanglement area law. And there are, at least in simple cases, we can have rigorous error bounds showing that this branching mirror works in relatively simple cases. Okay, so there is at least one ground state in here that you can prove the structure is the correct one. Okay, so between all of these different types of network, we've seemed to have got or properly reproduced all of the entanglement we expect to find, at least in common ground states. Okay. So we have the correct scaling of entanglement entropy. We want efficient algorithms for manipulating these structures. So with PEPs and mirror, we're doing pretty well. This branching mirror is still very difficult in practice. We want to be able to evaluate things efficiently. This PEPs, now exact evaluation is provably difficult. It's in sharp P complexity. However, we have very good approximation algorithms for getting information from PEPs. So usually in practice, it's not so bad. These other structures, 2D mirror and branching mirror, are things you can evaluate from efficiently order n time. Okay, so wrapping up here. So in practice, how good are these methods? In practice, PEPs is getting very good. Okay, so it was only a few years ago it was probably too expensive to be much use, but now algorithms are getting better, methods, everything surrounding it is improving and getting better, and people like Corbeau are having very impressive results for these very difficult problems like the 2D TJ model and Hubbard model that have been sort of long-standing, very difficult problems in condensed matter. This mirror structure is probably at this moment too difficult or too expensive to be viable for difficult problems. So we just need more algorithmic development, smarter ways to do the algorithms, smarter ways to contract things and do the manipulations. Okay, so let me just summarize. So our goal is to, at least we want this simple goal to begin with of simulating or finding ground states of lattice systems that have local interactions. Okay, and optimistically, I would say that this is something that seems to be within reach. Okay, we've got at least some of the way there, and it looks like this is a class of problem which is tractable to this type of classical simulation. Okay, so, and in general, hopefully anything sort of with a boundary law could be, or most things could be in reach to classical simulation. So what needs to be done? Well, I would say a lot of these 2D methods, we need much better practical algorithms, okay, so more efficient in how we do things, how we do these manipulations. We want better theoretical understanding, okay, so with 1D we have very good proofs and guarantees and provably converging algorithms. It would be very nice to have this type of thing in 2D as well, okay. And there is some work in this direction, like we can have some error bounds for PEPs, some error bounds for mirror in certain cases, but it's certainly nowhere near the situation in 1D where things are much more rigorously understood and developed. Okay, and We also want to move beyond these simple lattice models, so more realistic materials, so multiple orbitals per site, long-range interactions, so now you need to consider basis sets and things get much more complicated. And everything I was talking about was for ground state physics, so we want to be able to do dynamics, open systems, so other types of problem as well. And in particular, dynamics are much more difficult. You have this growth of entanglement typically, so these methods, at least the simple variants of these methods, tend to break down very quickly with this type of thing. All right, thanks for your attention.
So at the beginning, you started showing like how the memory requirement will grow with depending on the size of the, let's say, in quantum system you want to simulate. Do you have numbers for what these methods can do at the moment, like the 1D and the 2D? Just to have an idea.
So the idea behind all of these methods is that if you reproduce the proper amount of entanglement you expect in the wave function, then the cost is going to be in the system size, or like so. And in general, what we do is we just directly go to the infinite system directly. I mean, because if we have translation invariance, then we can just use the same tensor in each spot. So we're really not, we've shifted the problem of increasing system size as something we can get for free or very easy, but we need to be able to increase the entanglement. Okay, so the system size is not the concern, and there's no, it's really just we have a hill to get over for having enough entanglement. Once we're over the hill, we can do as big a system as we want.
So you are saying that these problems are not computational intensive, and you solve them? So your limit is the memory capacity, not the...
They are computationally intensive. It's just the system size is not the relevant parameter anymore. It's the amount of entanglement. So big system or small system, I don't care how much entanglement. So the prefactor before the area law becomes the important thing. But anything with the area law is in principle tractable now for large systems.
Can you say a little bit more about the branching mirror in practice? So is it a viable way to attack 2D problems, and what's known about it?
Whoops. The other way. Well, we can do. So in general, it's very difficult to optimize, I would say. Like in principle, everything's there and it's efficient, and you can show that you can reproduce the correct entanglement scalings and other things. In practice, I mean, it's just. So I would like to have a very good graduate student work on this for some time, and I think you would have a difficult project in actually implementing this, but it's something that could be done.
So, Glen, by difficult to optimize, you mean you don't have a good heuristic to go through the tensors as you have for, as DMRG does in 1D, or is that what you mean by difficult to optimize? You just don't sort of, don't know how to go through it? Or?
Yes, so my experience with this has been that it's much harder to converge in a proper way. Like you're trying to separate the physics off into two branches. So doing everything, like you have some methods where you can locally update each tensor, but trying to, that may not converge to the correct thing.
So the results that you mentioned for PEPs and the other thing, they just they sweep like DMRG sweep?
Yes, they sweep. This sweeping, yeah. So you could, and like ideally you'd have like say if I have some manifold of zero modes, one branch will be capturing some of it, one branch will be capturing the rest of it. In practice, if I try and optimize this, maybe one branch just tries to do everything and the other branch just does something trivial. And it's very hard to smoothly go between these two cases where one branch is doing something trivial to partitioning it. So the variational problem is much harder. I don't know whether this is amenable to doing just the local sweep over all tensors in general.
Ask a question. When you do this, you are trying to create a state. And you've been talking about characteristics of the state. But how do you know how close you are to the state you want? I mean, do you have a way of measuring that or knowing, besides you're looking at an attribute of the state?
So usually we're looking at the energy. So you can evaluate the energy of your state. You can evaluate how the energy scales as you increase the dimension of these indices. Whether it's going, you can evaluate the variance of the energy to figure out whether you're in an eigenstate or not. But in general, like, you don't have a guarantee.
Okay. Just a question of how you measure it. That's what you do.
In other cases like DMRG, you have very good. You can understand the truncation error more accurately. So it's sometimes the energy is not a good metric, but you have these other ones like related to how much error is involved in each truncation that you can have better understanding as well.
So actually following up, for these branching mirrors, did you say that there are rigorous results for some cases for showing that you can represent them, or
yes,
including also an algorithm for efficiently even for special cases?
So for these special cases, you can actually analytically come up with these tensors for different dimensions. It's based on some weight, like you can show that this relates to a wavelet transformation, and you can build solutions from known wavelets that have some convergence to the exact result. That's not variational.
So,
I'm not sure if the area allowed bounds affect this, but can you use these methods to efficiently compare good states or thermal states?
Yes, that's been done with these mirror and with these PEPs. You have to do something else rather than variational energy minimization, of course. So usually, if I have one way of doing this is by using a path integral formalism where you represent e to the minus beta h, so a path integral, and you have a way of turning this into the tensor network. Okay, so it's well, imaginary time evolution versions of these algorithms. Should we do one more? Sorry.
How difficult is to make these algorithms parallel on a typical supercomputer?
Usually quite difficult. So there are some things you can do in parallel, but usually the method you have for an ansatz is you sweep over every unique tensor and you go in a little bit in the right direction. So you can try and do different tensors at the same time, but you like parallelizing beyond, say, a few hundred CPUs is probably very difficult. It's not like Monte Carlo, we can go tens of thousands very easily.
So you mentioned dynamics as a possible future direction. Are there situations where you might hope that you could tractably simulate dynamics? I mean, I would somehow imagine that even for like gapped one-dimensional systems, typically it would be quite hard to do that with classical methods. But are there cases you have in mind where you think this might actually be something you could do efficiently?
I think it's not out of reach. I mean, many people have had proposals where they can do some types of dynamics efficiently, or even maybe you don't need to follow the dynamics. You just want the long, like the steady states or something. Mm-hmm. There are things that can be done. I don't think it's intractable.
So, thanks very much. That's Glen.